Define the term chemical equilibrium. I'm actually not reading the question, but telling you to define the term chemical equilibrium. That is 6.1.1. Let's take a look at 6.1.2. At T1, oxygen, O2, was added to the container. Write down the letter that represents O2. Choose from X, Y, or Z. Let's go through the question statement and see what is happening. So the reaction of carbon monoxide gas CO with oxygen gas O2 is investigated. The reaction reaches equilibrium in a closed container at constant temperature T degrees Celsius, according to the balance equation below, as we can clearly see here given to us. Changes to the conditions of equilibrium are made at different times. The graph shows the results obtained, X, Y, and Z. That represents the gases in the above reaction. Back to our equation. At T1, oxygen O2 was added to the container, rather than the letter that represents O2. So when we look at our reaction here, X, Y, Z, it should be easy to see that Z is what is added at T1, right? So that answers our question 6.1.2. We're supposed to write down the letter that represents O2 from X, Y, or Z. So the answer to 6.1.2, we have X. That is the letter that represents O2. Yeah, clearly there is a spike with regards to X at T1. Yeah, so clearly it is oxygen because that was what is added at T1, we are told. We're not supposed to give a reason, but I've sort of told you why that is. 6.1.3. At T2, the pressure is adjusted by changing the volume of the container. Was the pressure increased or decreased? How many marks? 1. Okay, I wish it was 2 or 3 because we really have to think. Well, 6.1.46 we must explain, so I guess the 1 mark is justified. So let's take a look at T2. At T2, X goes down, right? So O2 goes down at T2. And then we have one other substance, Y, that goes down, and Z that goes up. Okay, so we are told that the change that was made is with regards to pressure, right? So let's take a look at our reaction. On the right hand side, we have 2 plus, let me use something lighter. We have 2, okay, that is even worse. What is happening? We have 2 plus 1 moles of oxygen on the right hand side, right? You have 3 moles of oxygen on the right hand side, and then on the left hand side we have 2. Okay, why are we doing this? We want to sort of see how our reaction will react, how our system will react to a disturbance, because the system wants to oppose the disturbance, right? So what happened to O2? O2 at T2, it went down. Okay, so we're saying that the concentration of O2 goes down, okay? And then look at Y. Y also goes down. But after Y goes down, it doesn't bounce right up, because if you take a look at O2, O2 bounces up after it goes down. And then Y goes down, but keeps on going down. And then Z goes down, but bounces up together with O2, right? So because the change is with regards to pressure, we can say that O2, it's X, and Z is actually carbon monoxide. Z has to be carbon monoxide. So this is CO. And then Y should be carbon dioxide, CO2. So, okay, O2 did go down, but ultimately it went up. So let's change that. O2 actually goes up ultimately, because when the pressure is changed, right, they all go down. Now we can conclude and say that the pressure was decreased here. How do we know that the pressure was decreased? The pressure was decreased because the rate of reaction, the concentration of all the reactants went down momentarily, as we can clearly see here. So O2 goes down for a moment and then it goes up. Carbon monoxide goes down for a moment and then it goes up, as we can clearly see in the diagram that we're given, right? But CO2 goes down and stays there. It goes down and stays there. So the pressure was decreased here, right? And then as the pressure was decreased, reverse reaction was favored. Reverse reaction was favored. Reverse reaction is favored because it is the one that leads to more number of moles of gas, hence increasing the pressure. So what is our equation again? Was the pressure increased or decreased? The pressure was decreased. The pressure was decreased. 6.1.4. Why are we saying that the pressure was decreased? Reverse reaction was favored. Well, I'm not going to write. Let me just tell you. Reverse reaction was favored. And then reverse reaction, when it is favored, it leads to more number of moles of gas, hence increasing the pressure. The only way our system would react in this manner, where it leads to more number of moles of gas where the pressure is increased, is if there was a decrease in the pressure, right? So that is the answer to 6.1, 6.1.3 and 6.1.4. Right, they look like they all go down momentarily, but you have to see beyond that and see, oh, okay, well, O2 ended up going up, CO ended up going up, and then it is CO2 that goes down ultimately. So reverse reaction has to be favored. Pressure has to have been decreased because the reverse reaction leads to more number of moles of gas, hence increasing the pressure. Okay, 6.1.5. Let's take a look at that one. Write down the letter or formula of the gas that is represented by the letter Z. We already have the answer. 6.1.6. Give a reason for the answer to equation 3.1.5. Well, can I say we already have the answer? You know, can I say that we already have the answer? We already have the answer. Why am I saying that we already have the answer? We can see that when the pressure was decreased, the concentration of the reactants goes up, right? And we can see that concentration of X went up, which we know to be oxygen gas, and concentration of Z went up. It has to be carbon monoxide because that's the other reactants that we have. So write down the name or formula of letter Z, CO, carbon monoxide. You have the freedom of choice there. So that is 6.1.6. 6.1.7. What change in temperature is made at T is equals to 3? Choose between increase or decrease. T is equals to 3. So at T is equals to 3, O2 goes down. Carbon monoxide goes down. What does that mean? Forward reaction is favored, right? CO2 goes up, we can see. So forward reaction is favored. Let's go to our reaction and see whether our reaction is exothermic or endothermic. The forward reaction is exothermic, right? Forward reaction is favored. So it is the exothermic reaction that is favored, right? So which change in temperature favors exothermic reaction? Well, let's think. Endothermic absorbs heat, right? So if you increase temperature, endothermic is going to be favored so that it can absorb some of that heat, mitigating, right? And then if exothermic is favored, it means that temperature was reduced, and exothermic is favored so that it can release energy and the temperature can increase. So what change was made to the temperature at T3? If exothermic is favored, temperature was decreased, and if temperature is decreased, exothermic must be favored so that the temperature increases, because exothermic releases energy. That is 6.1.7, and we have answered 6.1.8. Use Lee-Chartgall's principle to explain the answer to 6.1.7. And now the elephant in the room, 6.2. Carbon monoxide reacts with water, H2O, at T degrees Celsius. The reaction reaches equilibrium according to the balance equation. We have carbon monoxide plus H2O to give us CO2 plus H2. And then we're given the initial number of moles of carbon monoxide, of H2O, of carbon dioxide, and of hydrogen gas. And then we're given the volume, which is 2 decimeter cube. How often do we find the volume of 2 decimeter cube? It's like it's an examiner's favorite, this volume of 2 decimeter cube. But anyway, stories. If the equilibrium constant Kc for this reaction at T degrees Celsius is 4, calculate the mass of carbon monoxide present in the flask at equilibrium. Okay, so let's go ahead and have our table, right? So yeah, obviously you can answer the question in the absence of a table, you know, but for the faint-hearted ones, me included in this case, let's use a table. Yeah, it's quite hectic when we don't have a table. Yeah, it's quite hectic when we don't have a table. Yeah, but it's doable. It's doable. I've been convinced that we can do it without a table, but I still prefer a table. Okay, so this is carbon monoxide. This is H2O, this is CO2, and then this is H2. The balancing coefficients, we have 1, 1, 1, 1, so we don't have to worry about that. And then here I'm going to put my initial number of moles. Here I'm going to put the change. Here I'm going to put the number of moles at equilibrium. Here I'm going to put the concentration at equilibrium. So the number of carbon monoxide that I start with is 0.6. H2O, 0.6. Carbon dioxide, 0.1. H2, 0.1. Our Kc is greater than 1, right? Our Kc is greater than 1. It is 4 actually, way greater than 1. So the forward reaction needs to have been favored in order for the Kc to be close to 4. That is the first thing that we have to see, right? So what will be the change? With respect to the balancing coefficient, here we can have minus x because the reactants, they're going down, they're getting used up. And then the products, we have plus x. So at equilibrium, we're going to have 0.6 minus x, 0.6 minus x, 0.1 plus x, 0.1 plus x. And then the concentration, we just divide by the volume. 0.6 minus x over 2, 0.6 minus x over 2. 0.1 plus x over 2, 0.1 plus x over 2. So Kc is equals to concentration of CO2 multiplied by the concentration of H2. Everything divided by concentration of carbon monoxide multiplied by the concentration of H2O. So what is the Kc? The Kc is 4. Concentration of CO2, that is 0.1 plus x over 2. And then H2, 0.1 plus x over 2. Everything divided by concentration of carbon monoxide, 0.6 minus x over 2, 0.6 minus x over 2. So let's solve for x. First thing first, 4 is equals to 0.1 plus x over 2 to the power 2, because they are multiplying each other, right? Divided by 0.6 minus x over 2, everything to the power 2. We can take square roots on both sides. I'm not going to write it down, but hopefully you can see that. You can see the consequence of taking square roots on both sides here. We will have 2 is equals to 0.1 plus x over 2, right? Everything divided by 0.6 minus x over 2. So 2 is equals to 0.1 plus x over 2 multiplied by 2 over 0.6 minus x. 2 and 2 cancels out. 2 is equals to 0.1 plus x over 0.6 minus x. So 1.2 minus 2x is equals to 0.1 plus x. So 1.2 minus 0.1, 1.1. Okay, I feel so stupid, but I don't want to make any mistakes. X plus 2x is equals to 3x. So x is equals to 1.1 divided by 3, which is 0.3667. What are we looking for again? The mass of carbon monoxide at equilibrium. So number of moles of carbon monoxide at equilibrium. Let's go to our table. carbon monoxide equilibrium, we have 0.6 minus x, is that right? So this is 0.6 minus 0.3667. Let me put that in my calculator. I get number of moles being equals to 0.2333 moles. So the number of the mass rather is equals to the number of moles multiplied by the molar mass. So we have 0.2333. Molar mass of carbon monoxide, I think just 12 plus 16. So multiplied by 12 plus 16. This is 6.53. So 6.53 grams is equals to, well, that's the mass of carbon monoxide at equilibrium. There we go.